In a similar way to alkenes, alkynes may be hydrated in the presence of dilute aqueous acid to give addition products. Subsequently, the enol addition product goes through a process called tautomerism to give a thermodynamically favored carbonyl functional group. The pathway for this process is really two mechanisms in one. Initially, the alkyne is protonated to give a carbocation in which Markovnikov regioselectivity is observed. Water then attacks as a nucleophile and traps the carbocation to form an oxonium ion, which is then deprotonated to afford an enol functional group. The enol is formally the addition of water to the alkyne. However, the enol is not the most stable possible product, so it undergoes a process called tautomerism to give the carbonyl group, in this case a ketone. Since the alkyne features electron-rich pi bonds, it is easy to protonate, so in the first step of the hydration process a pair of pi electrons is used to pick up a proton and form a carbocation intermediate. Since the starting alkyne is unsymmetrical, the proton may add to either carbon, however the preferred pathway is the one that yields the better carbocation. Water from the solvent then undergoes a fast nucleophilic attack on the carbocation to give an oxonium ion, which is actually a protonated enol. Deprotonation of the oxonium ion by water from the solvent gives the enol, which is the formal product of addition of water to the alkyne. The enol then undergoes a process called tautomerism, in which the pi bond and a proton change places, to give a more stable carbonyl group. The first step of this change occurs by protonation of the pi bond to give a carbocation. The regioselectivity observed in the enol protonation step is due to the attached oxygen being able to stabilize the carbocation through delocalization of one of its lone pairs. To complete the process, water from the solvent deprotonates the oxonium ion to leave the thermodynamically preferred ketone product. Overall, an alkyne will be hydrated in the presence of aqueous acid to produce a thermodynamically favorable ketone. For a terminal alkyne, the ketone will be the sole product, while for an internal alkyne a mixture of ketones will result.